Hello everyone, and in today's video lecture, you're going to see about what are the hardware techniques available for the enhancement of signal to noise ratio. And you can find this topic in the course of Instrumental Methods of Analysis. So, I'm Dr. Girija from the Department of Physics, Dr. N.G.P Arts and Science College, Coimbatore. In this video, we are going to see about 5 different hardware techniques used to enhance the signal to noise ratio, which in turn will pave way for enhanced or perfect output. The signal from input transducer should be sampled at a rate twice the highest frequency component of the signal, and which obeys the Nyquist theorem. So Nyquist theorem is also known as sampling theorem, and it is the principle that engineers follow in the digitalization of analog signals. So we have to adhere to this Nyquist theorem to obtain reliable results from either a hardware or a software enhancement methods of signal to noise ratio. What are the ways to enhance the signal to noise ratio? So there are 5 different ways how can you enhance the signal to noise ratio. So why it is necessary to enhance the signal to noise ratio is that we get a noise free output from different instrumentations available. Okay, so the ways you can use to enhance the signal to noise ratio is by filtering, by integration method, modulation or demodulation method, active filtering using tuned amplifiers, and boxcar integrators. So we go on one by one, and the first one is the filtering method. Here, the amplitude and the phase relationship of input and output signals can be used to distinguish meaningful signal and noise. So the frequency is the property most commonly used, but with respect to frequency, you can also use amplitude and phase. Noise can be reduced by narrowing the range of measured frequencies. The environmental noise can be eliminated by selecting proper frequency. So there are 3 kinds of electronic filters, and you can use them to select the band of measured frequencies. So the electronic filters, they are rather the low pass filters or high pass filters and band pass filters. So low pass filters, they allow the passage of all signals below a predetermined cutoff frequency. And high pass filters, they transmit all frequencies above a cutoff point. The band pass filters combine the properties of the low and the high pass filters, and they pass only the narrow band of frequencies. So you can see here the graph of signal and the frequency, the magnitude, how the signal varies with respect to the frequency for a low pass, for a high pass, and then band pass or active filters. Okay, so we can see the curve where the signals are transmitted and where it is blocked, and here in the band pass you can see the blocked signals and where the signals are allowed to transmit in a particular frequency. Okay, so the simplest filters, they are composed of passive circuit elements. So passive circuit elements in the sense resistors, capacitors, inductance coils, and with the transmitted frequencies which are determined by values of individual circuit components. So why you can see it in the figure 2.6 here. And bandpass filters can be designed using op amps or operational amplifiers. So in this 2.6, you can see the different types of circuit designs of low pass filters, high pass filters, and low pass filters, where you use the resistors and capacitors for the working of different kinds of filters. And next comes the integration. So integration of DC signals for limited time period is a powerful way to reduce white noise. So you have different types of noise, and to reduce the white noise, you can use this integration method. So actually, what is white noise? It is a steady, unvarying or unobstructive sound as an electronically produced drone or the sound of a rain, used to mask or obliterate unwanted sounds. So this represents a white noise. Or in terms of physics or science, you can define it as the random noise with a uniform frequency spectrum over a wide range of frequencies. So the coherent or non-random signals adds directly with respect to the integration time, whereas the random noise adds as the square root of the integration time. Therefore, the S by N ratio or signal to noise ratio increases with the square root of the integration time. So although we use a simple RC filter as we saw in the figure 2.6, you can use it to integrate signals, and an operational amplifier with a capacitor in the feedback loop. They serve as an hardware integrator. So analog to digital converters such as voltage to frequency or dual slope devices have been built in S by N ratio enhancement by using integration techniques in signal conversion circuits. Next method comes the modulation and demodulation. If the signal and noise cannot be separated by filtering method, it is good to shift the signal of interest away from the noise frequency. And if you want to do this or accomplish this, the signal is first transferred or transposed onto a carrier wave, which has desirable frequency. And then it is transmitted to an amplifier tuned to frequency of the carrier signal, and finally to the original signal, or the original signal is recovered from the carrier wave. So the first process is known as modulation, and the final one, the demodulation. So modulation or the demodulation technique can be used for the process of a signal in the region of minimum noise, and also to distinguish them between the signal to noise on the basis of signal's unique modulation configuration relative to random pattern of the noise. This technique can be used to reallocate signals away from the DC where flicker or the small noise is at the maximum. So examples are the frequency and amplitude modulation used in radio broadcasting and in optical spectrophotometers. Example, one more you can go on. The chopper in the spectrophotometer must be located as close to the source of radiation as the modulation removes only the noise arising from the chopper. So what is a chopper? It is an electrical or mechanical device used to generate a signal alternating between the sample and the reference measurements at a frequency selected to minimize noise. Next method, we go on to the tuned amplifiers or the active filtering to enhance the S by N ratio. Though signal is processed in a noise-free environment, noise is present due to two reasons or factors. Bandwidth required to transmit the signal, and during the process of matching signal frequencies and bandpass filters. To overcome these problems, phase-sensitive amplifiers or log amplifiers can provide us the solution. So combinations of signal frequency and phase relationship discriminates between the flicker and the white noise. So what is flicker noise? It is a type of electronic noise with a 1 by frequency power spectral density. It is therefore often referred to as 1 by F noise or pink noise. So the functional components of a lock-in amplifier include modulator, which is also a chopper, a multiplexer, and a low-pass filter. Okay, we can view it in a figure 2.7. The lock-in amplifier is a type of amplifier that can extract a signal with a known carrier waveform and extremely in a noisy environment. So this is a lock-in amplifier where you can find it in the absorption spectrophotometer. So you can see where the chopper is present, and the dotted lines represent the lock-in amplifier where you have a multiplexer and a low-pass filter, and the monochromator, the detector, and the reference source. So this is the block diagram of a lock-in amplifier. Now the data containing signal at frequency f is superimposed onto carrier wave with frequency f0, so which produces a modulated signal f0 plus delta f, which is transmitted to an electronic device called multiplexer. So delta f is the frequency containing the desired information. Simultaneously, a reference signal or the modulated at same frequency is at the carrier signal. That is, when this is happening, a reference signal is also modulated at the same frequency as the carrier signal. It is held constant in phase with the carrier wave and is sent to the multiplexer. Multiplexer can demodulate the combination of carrier and reference signals to yield a waveform at 2f0 plus delta f. So delta f will be a low frequency data and can be extracted from 2f0 using the low pass filter. The band pass of transmitted frequencies can adjust, or it can be adjusted by varying RC time constant of the low pass filter. These operations transform original spectrum of information frequencies delta f, which is centered at carrier frequency f0, to the same spectra containing delta f, which is centered at the DC, which is 0 Hz. When the carrier and the reference waveforms occur at the same frequency and constant phase relationship, the desired information minus the noise will appear in the transformed spectrum. So this method of noise reduction is limited to data containing signals that are periodic. If the signals are rapidly changing, other enhancement techniques must be used. So why we are going for other techniques? The low pass filter is centered at DC. Some flicker noise will be present in the lock-in amplifier system. So phase sensitive detection is used in spectrophotometers to achieve an increased S by N ratio. The final method is the boxcar integrators. This is a simple method of signal enhancement for repetitive signals. This periodically samples the same portion of a signal for fixed period of time and then averages the samples using low pass RC filter. And this provides S by N ratio enhancement for the portion of the signal that is sampled. So this technique has a wide application for instruments that require pulse signal detection. So when compared to average value of a single pulse, this boxcar integration gives S by N enhancement equal to square root of the number of pulses integrated. Noise also accumulates during sampling time. So further increase in S by N ratio results from shortened total sampling time of the boxcar method as compared to the time required to average a single. So in conclusion, we came to understand why the Nyquist theorem is used to enhance the S by N ratio, and what are the ways how to enhance this S by N ratio. We came across, we discussed 5 different methods, starting from the filtering, the integration, the modulation, demodulation, active filtering, and finally the boxcar integration or the boxcar method. And these methods are commonly used to enhance the S by N ratio and instrumentation to get a noise-free results from different various instrumentations used. Hope you enjoyed the video lecture. Thank you all.